do today is a little bit different from how I originally planned, but one of the stats classes lost today because of technical issues, and then I had to end up going to the dentist, which was planned, but the technical issues wasn't. So what we're going to do is I'm going to start chapter 2, and we're going to go through chapter 2, and those people who that's all they needed, they can just leave at the end of this. I'll tell you when I finish chapter 2. And if once that's happened, I want to go back and I want to spend some time, because I had at least 3 emails from people saying, look, I'm having a real hard time with these cumulative frequency graphs, these OGI curves, and I want to do another one of them, like from start to finish, so that you can get help on that. And that will be kind of today's work. So let's get started. Chapter 2, the part that we're dealing with is the second half of it, is to do with how do you draw diagrams and charts of qualitative data. So qualitative data is data that's typically non-numeric, right? Red, blue, green, I agree, I disagree, I'm a junior, I'm a senior, anything that's non-numerical. And we know that this type of data falls into 2 distinct subcategories. In no particular order, one of them is called ordinal, and the other kind of data is called nominal. Just spell that right. The beginning of the word does give you a clue. One of these, although the data is not numbers, it still has an order to it. So for instance, if you were looking at private, sergeant, lieutenant, and general, right? So if you were collecting data on what rank a person had, the answer would be sergeant, lieutenant, general, but would you also agree that they have an order to them? If you were collecting data on high school students, you get the sophomore, the junior, the freshman, and the senior. Would you agree in those cases, it has a natural order to it? And that type of data is called ordinal. And the other type is called nominal. And nominal is like red, blue, and green. Apart from alphabetic, which you can do to every kind of data, there's nothing really special about red should be before blue or blue should be before green. Right? So in both these cases, this type of data anyway, there's a limited number of things that we can do to them graphically and in the form of charts and diagrams. So we're looking at the first kind of way that you can collect this data is basically just a frequency table. And I'm just going to cut to the chase here and show you what a frequency table might look like in these situations. So you went and asked a number of, we'll do the children's colour thing. You asked a number of children what their favourite colour was. And we got red, we got blue, we got green, and let's say yellow for whatever reason. The second column will be called frequency. And essentially what you have here is 3 of them light red, 11 light blue, 5 light green, and only 1 of them light yellow. Now, this is basically a frequency table. That's what it's called. You sometimes get what's called a relative frequency table. And what you do in those cases is you add a 3rd column called the relative frequency. In this particular question, you need to know the total number of people who were asked. In this case, it's 20, right? And to get the relative frequency, you take the frequency and you divide it by the total number. So although the answer as a fraction would be 3/20, we don't really like fractions. They're very clunky things to deal with. So you either turn 3/20, which is this guy here, you leave it as a fraction, or you turn it into a decimal. And it's quite common, I think I'll go back to red, it's quite common that you use a decimal, right? So 11 who liked blue, the relative frequency for that would be 0.55. For the green, the answer would be 0.25. And lastly, the unhappy yellows, it would be 5.5. So that would be called a relative frequency table. So you see what I'm doing here is kind of doing two tables at once. If you needed to create a frequency table, it would just look like that. If you needed to do a relative frequency table, you'd have an extra column. And another thing, sometimes the relative frequency is written as a decimal. In fact, it's very often in that way. But occasionally, because I guess they want to, I'll just go back to green. Sometimes they'll ask you to do it as a percentage. I'm all happy about how to turn decimals into percentages. You just multiply the decimal by 100 and you're done. Now, you wouldn't normally have both. You'd either have the decimals or you'd have the percentage. I don't see any situation where you would actually put both in. So it depends what they ask. If they want a relative frequency in percentage form, you do the green guys. If they wanted a relative frequency without mentioning anything, you would do the decimal guy. So far, so good. It's pretty much what one of these tables can look like. For this type of data, you are limited in a lot of ways to what you can get from it. The simplest things you can get are 11 is the most popular color, yellow is the least popular. And you can say 55% of people like blue and only 5% like yellow. You could say it in that format. But apart from that, you can't look for patterns, because for a pattern, don't you need things to be in order? So you can see things going up and things going down. Well, if you can jumble them up in any order you like, couldn't have done this table blue, green, yellow, red, and it wouldn't matter. It'd have the same information. So you don't really talk about patterns, you know, like we did in the other kind of data where it would be skewed right or skewed left. That has no meaning here. So that's pretty much the end of how this data, and it doesn't matter if it's ordinal or nominal, the table looks the same. There's no real differences. So what kind of diagrams can you get? Well, you can get a guy called a bar chart, and I call it a pie chart. I believe this textbook calls it a circle chart, or something very close to that. Let's look at the bar chart. You have horizontal and vertical axes. Along the horizontal, you typically put what the variable is. In this case, it's favorite color of children. And then vertically, vertically you do the frequency. And you choose a scale. Since my biggest number is 11, I'm keeping my fingers crossed here, I can get away with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I good or am I good? 11. That was more luck than anything. Now, for each one of these, you simply just pick a start point wherever you like, and maybe, I don't know, say 2 boxes wide, 3 boxes wide, whatever you feel like. And that's the start and the finish. And for red, you go up 3. And then you tell people it's red. And if you want to, you can shade it in. If you don't need to. And that would be that one. Then you leave a gap. And then you start and you do 2 boxes worth. And that's going to be blue. And you go up to 11 and you go across and you come down to 11. There, that's blue. And you start here and you finish here, and this can be green. And green is what, 5, so it takes you to about here. And then you have a little gap again, and poor little yellow looks like that. And that's basically a bar chart. And I don't know, I'm trying to think, I'm that old, I can't remember. I think I probably did bar charts when I was 9 or 10 or something. I mean, way back. It's probably the first charts you ever did. So the features that you need are little gaps. And do you notice that the height of the rectangle basically represents this? Now, how would I do a bar chart, but using the relative frequency, right? Using these red decimals. Well, all I would really do here is, darn it, I wish I didn't need an eraser. Here is my eraser. You just choose a different vertical scale. So can you imagine this guy here would be 0.55. Oh, you can't see it. This guy here would be 0.55, and then I would probably be going 5, 10, 15, 20, 25, 30, right? Things like that. And you would just choose a scale and you draw the same thing. The result is, wouldn't a relative frequency bar chart and a frequency bar chart have the same basic shape? If you chose the right scales, they might even look identical. But see if you choose a slightly different scale, couldn't it be the same shape, but maybe half as high or twice as tall? So bar charts can use frequencies, bar charts can use relative frequencies. I don't think we're going to get too many, I hope, too many issues with that, right? You get what you get. So let me introduce you to another chart. It's called a parental chart. And I will come back to that because I forgot one very important thing. If my data is nominal, can I basically rearrange the red, blue, green, yellow, pardon me, any order I like? And it's the same piece of information. But if the data is ordinal, shouldn't you choose your rectangles and arrange them in whatever that natural order was, right? So I'm going to imagine I created a table. Oh God, you think I would remember, but I can't. The 4 different names you give to high school students, like college students, that name, right? The first one, freshman. Yes, okay. F for freshman, right? And there's how many that ends up being, right? Right, after freshman, you leave a little gap. What's the next one after freshman? Sophomore. I see your lips move, so I'm going for it. Sophomore. Sophomore. I can do the next two. Junior. And then senior. So can you imagine this just might be a particular high school, and you found out how many freshmen, sophomore, junior, and seniors there were, right? Now, in this case, it's still a bar chart, right? It still has all the same features, right? That might be 10, 20, you know, maybe it's a bigger scale because the numbers were much larger, but it's got the basic same structure, right? So this would be frequency. Try to think of what that would be. Position in high school. I'm not sure if that's the right way to phrase it, but you know what I'm trying to say, right? That's what ordinal looks like. The only difference, you must put them in order because that's a sensible thing to do. Right, now I can talk about parental charts. These are special versions of bar charts. These are bar charts where you put the data in order, typically highest to lowest. So let's suppose I collected data and it was on movies. And we asked people in our sample, what kind of movie do you like to watch? Right? And so some people say, my favorite kind of movie to watch is a science fiction movie, right? Other people say I like to watch war movies. And some, probably my wife would say I love to watch love story movies, right? Girl flick movies. I love to watch animations. I love animation movies. I just think they're cute. I'd watch any of them. I don't care what age they are. I like them. I'm running short of some ideas. I need 2 more headings because my brain's kind of drying up. Give me a couple more genres of movies you might watch.
You could do horror. Yeah.
Say that again?
Horror.
Oh, horror, definitely, yes. Especially at this time of year, right? We're coming up in that time of year where horror movies start becoming popular. What are they up to? Freddy 42 by now? You know the Freddy movies? There must be about 42 of them. Okay, we need one more just because I've got an empty box.
Sports movies?
Sports. Yeah, things about,
Movies.
you know, teams, boxers, football teams, you know, the rise to fame, the Rocky kind of movies, whatever. Right, so since I'm in charge of this data, actually I'm not in charge of this data. Let's try and make it vaguely realistic. Right, I'm going to close this off for a second and we're going to collect data from everyone here. So there's a little guy in the right-hand side called reactions. And if you click on it, you see the thumbs up thing. So we're going to do that as the voting system. So here's the rules. You can only vote for one category. I don't care if you like all of them. You have to pick the one you like just a little bit more than all of them. And if you hate all of them, you pick the one you hate just a little bit less than all of them. Or you just don't tell me anything and that'll work as well, right? So here goes. And I'm counting myself because I'm allowed to vote. Sci-fi. Stick a little hand up and I'll, I don't want to be alone here. Okay. 1, 2, 3 of us. Okay, 3 like sci-fi. How many? Oh, 4 like sci-fi then, right? How many like war movies? Okay. How many like love movies? Girl flick movies? Romance movies? I'm trying to think of other names for them. Yeah, gotcha. How many love animation? I wish I could have voted, but sci-fi is my favourite. How many like animation? Got 2 of you. How many are into the horror genre? 1, 2, 3, 4, 5, 6. And last but not least, are any of you like watching movies about sports? No. Good grief, that can't be. Some of you are voting twice. I'm waiting for it to disappear. Okay, we're getting 6 here. That's a lot of data. So what have I got? 6, 11, 12, 13, 25. Now this data, is it nominal or ordinal?
Nominal?
Right, correct. There's no, I mean, science fiction is no more or less first than last in any of the others. But I can still do a parental chart of that. What I need to do, and I think I'll move it over here because I want the room, is that we do our vertical axes, right? And we do our horizontal. And along we do, at the bottom we tell people it's favourite movies. And vertical, it's going to be frequency, as you'd expect. And you do it in order.
Chart.
Oh, okay, that was, thank you. I forgot. There we go. You see it now? Right. So favourite movies, frequency, this is our data. So the biggest one, well, I guess, unfortunately, just as life would have it, there's 2 6s. So we'll just have a compromise. 1, 2, 3, 4, 5, 6. There we go. So you draw one of them and then a little gap and you draw the next one. And I guess we can't really do much about that. You just H for horror, S for sports. Right, that's them taken care of. The next one is the loved ones. And there's 5 of them. So you go little gap and you do this guy and you put love movies. That's that one done. Next one is sci-fi, so There's 4 of those. And then, oh, there's another draw at the end, war and animation. So, war and animation. And when you draw this, it's called a parental chart. It's really just a bar chart, but it's a bar chart where the data is put in order from most popular to least popular. It kind of makes sense. Would you agree that if you wanted to do anything, probably that's the best you could hope to do, wouldn't it? From best, most popular to least popular. So you can scan from left to right and see quite clearly what's going on. Is there any questions about a parental chart or about a bar chart or any of the other stuff that we've done so far? Are we good? Right. Now, the next diagram, graph, I'm trying to think of a word for it, is going to be the circle. I call it a pie chart, but I believe they call it a circle chart. I think almost everybody that I know calls it a pie chart. You know what I'm talking about when I say that? You've probably taken a geography class and there was a pie chart in it about the different things that are growing in a particular state or something, right? So I'm going to use, because it's a good idea if you can, just to use stuff more than once. I'm going to use the data from my sci-fi, right, this thing here, to show you how you would create a pie chart. So I've got the movie. We've got the frequency. We're going to calculate the percentage relative frequency. And then we're going to calculate the angle that you would use in your diagram. So we need this diagram here to help us to draw a pie chart. So here's the sci-fi. Here's the war. Here's love. Here's the animation. There's H for horror, and we'll need one more obviously now. And there's sport. The total here is 25. So it was 4, 2, 5, 2, 6, and 6. Now the relative frequency would be 4 out of 25. I'll write the calculation down only for the first one. Now 4 out of 25, if you go to your calculator and you want to make that a percentage, the quickest way to do it is just go 4 divided by 25, which is that guy, and then multiply everything by 100. So what you get here, make it green, is that guy there is 16%. If you want to know what 2 out of 25 is, the answer ends up being 8%. If you want to do 5 out of 25, it's 20%. I know this guy because I already got it, is 8%. And if you do 6 out of 25, it looks like you're looking at 24%, and finally 24%. Are you all happy about where I got the relative frequency but the percentage numbers? And the reason I need these is to get the angle. And I'm going to pretend, and that's all I'm going to do, is that that's a perfect circle and that that's the center. And that I'm going to start with a horizontal line. Okay, so 16% of what people like out of the total, 16% like sci-fi. What is a complete circle? Well, it's 360 degrees. Great. So when I want to know what angle, what piece of the pie does science fiction get, it gets 16% of the pie. which means it gets 16% of 360. Now, if I want to get 16% of 360, I could just go 0.16, which is what 16% is as the decimal, and then just go 360. And I get 57.6 degrees. Now, I want you to imagine that you had one of these little plastic things. I don't know the last time you saw one, called a protractor. You know the thing? And you placed it over here and you measured to where the best guess you could get, and it's going to be a guess because it's not that accurate, right? Where 57% would go. And what you would then write is sci-fi, and then you would write 57.6% next to it. You could also write.
Wait,
4.
would it be not 57.6%? Would it be 16%?
I am so glad people are paying attention. It would exactly be that, yes. The 57 is the angle size. They might actually, I'm just thinking the reason I might have put that in is that the only one question, so I'm doing all of this just so you can do one blinking homework question. I think the only question you've got to do in homework, they tell you is a percentage. So it might well be in the homework one, it does say 57.6. But in real situations, you would normally say 16%, or you would say it was 4. Right, now as I go through the rest of these, can you imagine I get the percentage, the angles for the others? I'm going to try my best to see if I can do this quickly. 57.6, if I divide that by 2, this one's about 28.8 degrees. If I do 20%, I think it's 72 degrees. This one is 28.8 degrees again, and I'm doing the 24. And that's 86.4 degrees and another 86.4 degrees. Why am I doing percentage symbol that's degrees? Right, if I got my protractor, you use that as your new starting point. You'd probably get your piece of paper and make it horizontal. You'd measure off a 28 degree, and it'd probably be something like that-ish. And you do what? And then you do 72 degrees, and it's something like that. And you put in love. Then you do 28 animation, and it's something like that, and you put animation in. And then you do the last 2, and one of them here is horror, and the last one is sports. And you can imagine around each one of these, you would be putting either the percentage that was used or the raw data score. Right. These are not designed for human beings. We do not do good at drawing circles or measuring answers. Would you agree? But the one question that you get, which I'm going to show you in a few seconds from now, you could probably look at the pictures that they give you, because they give you 4 pictures and you just pick the right one. You could probably figure what that was without you physically needing to draw your own. So let's see if I can find that guy, and then I'll switch to it and show you. I know it's around here somewhere. I know you're around here somewhere. Come on. Here we go. So the only question that has them is this one here. And it does have percentages, that's good. Now, where do you get the data to decide which of these is your 4 pictures? Can you see the data is in this table? Right, so I can tell you the story behind this, but since it is only one question, and I really do want you to fill in it, you know, so that you can at least have one shot at doing it, right? But essentially, Commercial digging operations in ancient rivers occasionally uncover archaeological artifacts of great importance. One such artifact is a Bronze Age spearhead recovered from ancient rivers in Ireland. And these are rivers in Ireland. These are how many spearheads have been found in these. Right? Now, if you look at this particular thing, if you want to do a Pareto chart, remember the Pareto is biggest to smallest. Wouldn't you do Shannon first with 36? So if I scan through these, can you see the right picture is Shannon first with 36, right? Now, between this one with Shannon and this one with Shannon, can you see that this one has got the right walking down some steps look to it? So all you would do is pick, well, yeah, oh, actually I can. You can pick the dot. So you physically didn't need to draw that one, but can you imagine if you drew it, you could then go and look at your picture and say, yep, mine's looks like 4. Now, to get this guy, let's just pick one particular fella. We pick Shannon. Right. Now, if I go back to the original data, what do I know about Shannon? I'm writing this down, but you can just hear me say it. I know that there was 36 in the Shannon River, and the total number is 26. Sorry, 36, 41, 50, 60, 71, 77, 87, 93. So let me nip out and in and show you my calculation. What I'm doing right now is just for the Shannon River, and it was 36 out of 93 times 100. And on my calculator, 36 divided by 93 is that guy, times 100, and it looks like it's about 38.7, right, %. I would then go back to that picture, because I really don't want to spend all day trying to draw one of those charts if I can find a kind of workaround. I would go back to that and I would say, okay, out of those 4 pie charts, which one has Shannon about 38.7 degrees? And I have screwed up. So I'm going to have to count again. 20, nah. I'm going to use a calculator. I ain't going to do it. 20, add 6, add 15, add 36, add 14. And I got 91, not 93. And that's why my answer was wrong. So 36 divided by 91, the right answer should be 39.6. One of these guys should be 39.6, and there we got him. And that's it. Pie charts are done. Are we cool? Right. Let's look at a couple of Pareto charts, and then we can move on to a totally new type of chart, ones that involves data. Okay, in the Aloha state, oh,
Hawaii.
in Hawaii, oh
Yeah.
yeah, take me a minute there. In the Aloha state, you're very unlikely to be murdered. Well, that's nice to know. However, it is considerably more likely that your house is going to get burgled, your car could be stolen, or you get punched in the nose. Okay, so evidently people in Hawaii won't kill you, but they'll beat you up and steal stuff. Okay, everybody to their own. That said, Hawaii is still a great place. Yeah, it's better than being killed, you're right. So here are the numbers represented as per 100,000 population. So every 100,000 people in Hawaii, 3.6 are going to get murdered, 25 and a bit are getting raped, 84 and a bit are going to be robbed, 856 houses are going to be broken into, and 543 vehicle thefts, and 138 times you're going to get punched in your nose, evidently. One of these 4 pictures, and very often it takes you longer to read than it does to do, is a parental chart, right? A parental chart of that data. Now, when I look at this data, can you see that they're all doing the right thing and they're all going downhill? If I look at the data, the biggest number, I believe, is motor car theft, right? Let's check that. House burglary, no, house burglary is 85, right? So it's house burglary. Oh, okay. Well, that didn't work. And what number was it? 852.6. Oh, that's easy now. Isn't the only one of those 4 pictures that has the correct height for houses being burgled, which is 852.6? Isn't it that one? So, as I say, you'll spend more than half your time reading it. And then they go on to do some stuff to do with circles. Here's another parental chart about things. And I think that's us finished with the non-numeric data. Is there anything else you want to know about non-numeric data before we continue? You feel you're comfortable with bar charts, parental charts, pie charts? Good, me too. So let's look at the next thing. Let's look at quantitative data. We have covered some of the things that you can do with this type of data. We're going to look at some other things that we haven't covered now. We're going to return to data that is normal, that is numbers, which is the kind of normal data that you get. Vast majority of data is how old you are, how much money you've got, how many children you've got, how many car accidents you've had, whatever it might be. And there is a number of different kinds of other diagrams that we're going to look at. So in no particular order, there's a time chart, which is one of its names. It's also called a time series. Well, they're calling it a time series graph, but time series chart, time series graph. I think I've covered all the obvious names. We're going to look at another thing called the stem and leaf. Don't think it has got any other names. At least I don't know of any other. I'm just checking in case it has another name that I've never heard of. Nope, that's nice. Only one name, stem and leaf, which is good. And there's 2 flavors of stem and leaf, typically. There's 1 row per stem, and then there's 2 rows per stem. Okay, so what shall I do? I think I'll do time charts first, because there isn't any particular order to these. Right. Time charts are when you are given data where it's the first variable is time. So you can have data like, let's suppose you collected data and you broke the year into week 1, week 2, week 3, week 4, keep going to, I guess I run out around week 6, right? So you had a little 6-week window. And in that week, you found what was the maximum temperature it got on any day, day or night in that week, what was the hottest it ever got. And you just recorded that, nothing else. And it was 90 degrees. And in week 2, it was 80 degrees. In week 3, it was 75 degrees. In week 4, it was 60 degrees. In week 5, it was 40 degrees. And in week 6, it was 50 degrees. When you have data like this, do you notice that the second column is not frequency? It's not how many times something happened. Isn't that just a single number representing the best, in this case, the best temperature, the hottest in week 1, the hottest in week 2? Now, what one of these guys looks like goes something like this. Along the bottom, you choose a reasonable scale. And you put what that is. In this case, it's the week number. And then vertically, whatever was being measured. In this case, the maximum temperature. I need to go up from 40 to 90, right? So 10, 20, 30, 40, put in 50. 60, 70, 80, there's 90, I'll put in 100. And if you've never done one of these, I think you probably have a really good guess at what I'm about to do. Do you think you've got a really good guess at what I'm about to do? So let's see if it matches what you think. In week 1, you just put a dot at 90. In week 2, you put a dot at 80. So I guess I should put that in. There we go. At week 3, you do 75, which is about here. In week 4, you do 60, which is here. In week 5, you do 40, which is here. And in week 6, you do 50, which is here. And then you basically, you try the best you can to just join the dots up. And what you're doing here is visually representing the same information. But most people find that easier to see what's going on. Can you see that there was a pretty much steady decline until week 5, and then the temperature picked up a little bit? Can you also tell that the decline is maybe not the same, but it's roughly about the same amount? It wasn't really steep and then not so steep. It was kind of, give or take a little bit, about the same amount of decline. So you can look at these and you can interpret week 1 was the hottest out of that entire lot. Would you agree? Week 5 was the lowest. That's easy to see. Can you also see patterns in things? Now, I'm not going to do a real one because it would take too long, but can you imagine I did one where we did it for the 1st of January was called day 1, and December the 31st was called day 365, and we done the best temperature in every day. So it would look something like this. And I'm just putting in that. And I might put in (32) as well. And just because I could, you might even put a little dotted line here. And can you imagine the data look like this? So let's do green. If you have enough dots, won't it almost look like a curve? Now, what can I tell you about this place? Well, if we know that that's basically January the 1st, right? And this is December you know, the end of December, December the 31st. Can you see that this, you can almost tell, can't you tell where winter is? And can you tell that in this place, it's got a really good summer? And the summer lasts, well, I'm not even saying that summer, I would think summer's better than that, but doesn't it have quite a big chunk of months where it's 100 degrees all the time, every day, hottest temperature? And can you imagine that what would be used for this? And you could do it right now. If you wanted to go on holiday to Las Vegas, and you wanted to know what, I like heat, which I do, what month you should go in, couldn't you go online and they'd have a thing like this and tell you the entire average temperature in Hawaii and whatever it is, Las Vegas, Hawaii, or wherever it is. I don't know an awful lot about Hawaii, but I believe this is Hawaii. Isn't Hawaii like 80, give or take 5 degrees all the time?
It's really humid too, so that like makes it worse.
Well, yeah, this chart doesn't show humid, but can you see the blue line for Hawaii doesn't really do much? Isn't this a place that has definite seasons probably? Definitely got a winter and a summer at least. And you could look it up and you could find out, oh, the hottest time, I believe actually for Vegas, the hottest is August. So if you want to get really, I told you I was at Las Vegas, didn't I? Me and my wife and sister-in-law and brother-in-law, we went to Vegas for 9 days and it was great. Every single day was in the 100 teens. It was 113, 114 for 9 days solid. And we were at the swimming pool every single day. And it felt like I was a normal human being. I like that. I would go back right now if it wasn't for you lot interfering with my life. Actually, if it wasn't for you lot, I wouldn't have a life because I wouldn't have any money, so I can't really be too nasty to you.
Also,
Even
you
if I
could, you
wanted
could do
to.
the Zoom call from Vegas.
Yeah, this is true, but I'm not giving stories away here. There is a professor who lives in Vegas and does all his classes online, but he did that before COVID. So you are right, I could actually teach in Vegas and stop putting that idea in my head. Because I don't think, well, I would like it, but I'm not sure my wife would like me to disappear for 6 months down in Vegas. I don't think she would anyway. Okay, are we happy with how these time series things work? We cool? How this becomes that guy. And then you might get asked a couple of questions to do with that. If there aren't any more questions about this particular guy, I'm going to call that one good and move on to the next one. So this is kind of your last chance to say, you know, I'd like to know more about it or not. Okay. I'm going to show you what one of these guys looks like as homework. The data that we got here is how does the average height of boys change as boys get older? Well, obviously they should get taller, which I'm pretty clear that they do. So 0.5, that's 6-month-old boy, and that's a 9-year-old boy. So we're talking young kids, right? And it's this darn graph. I have no power over this, but I totally do feel your pain. This is very clunky to use. But I'm going to use this to create a time series, right? You're going to use this same process to do an Ojai curve later on today, right? So when I do, for those who need it, when I do the Ojai curve, you're going to see me use a diagram just like this. So 0.526, you hit this button here. You're seeing what I'm saying before, right? You're seeing this chart, agreed? Okay, so you hit this button here, and you see the one that has a dot and a line join in it? That's your go-to guy. Don't hit anybody else but that. So you hit them, right? And now 0.5 is about here, roughly, and 26 is sort of about here, so I click a dot, And then the next number is 1 and 29, and I'll hit a dot. Now, do you see those two guys are joined together as the beginning of my time series? I'm now going to go over here to segment 1, and when I click on it, it's going to tell me where I was. Well, do you see I was a little bit out? I thought I was hitting 26, but I really hitting 27. Do you notice that I can now change it by just going there, clicking on the box and typing in 26? What about the next point? Well, it should have been 1,29, and I did 1,30. So do you see I can now click on that and make it 29? So when I click out of that, well, when I close it off there, I've now fixed it, right? Now, here goes. Back in again, second set of dots. I'm going to go from 129 to 233, which means I have to start all over again and click on that guy, and then finish on 233, which is about here. Now, if I click on segment 2, that guy should have been called 129, so I'm now fixing it. And, oh, I got lucky on the second one. Done. Are we getting a feel for how you create this thing? It's a kind of slow process because I keep having to tweak it. I might get better on the next one. 233, which is here. Click on it and go to 336. 336 here. Check it out. Tweak it a little bit. Fixed. Next one. 336 to 449. Click on top of that dot and 439. Let's see how close I was. Hey, eventually you're going to get one right. Get ready for the next one then. We're going to go from 439 to 542. 439, gotcha. 542. Go that one. Next one is 625. 645, sorry. That one. I forgot, you have to fix it. So 439, good. 5, there we go, 42, done. Start again. 542 is good. 645. I'm sure darn it. Oh, here's another way of fixing it. Do you notice I know that dot's a little bit high? And you see when the mouse pointer is on it, it tells me it's 646. If you keep your finger on it, you can actually move the little darn thing around and then leave it when it's on the right number. So that's another way of fixing its location. Almost done with this question. We're going to go from 645 to 747. Yep, fixed it. Go to the next one. 747, gotcha, to 850. That looks good. Last one. 850 to 952. Ah, hey, I got kind of better towards the end. And we are done. Click anywhere I like. Go. There we go. And then you just hit submit. It is very fussy. See if just one of those dots was an 8.5 and it should have been an 8 or something like that. It would just tell you you're wrong. So it is a bit messy. But that's how you do a time series on this fella. So let's move on to our next, actually the last thing that we need to do. And then it's Ojai curves for those people who want to stay behind and hear about them. So I don't know where I am in this here. I do know. The last kind of data diagram is called a stem and leaf. What does a stem and leaf look like? Well, I guess the best way to show you is to do one. Okay, and let's collect data. And this time I'm going to collect raw data. So the rules of this game is you tell me what your age is if you want to. And if you don't want to tell me your age, you simply just don't tell me anything, right? And I will very quickly move on to the next person. You can do what my sister does. You can lie. My sister was 31 for a very long time until her first son became 31, in which case she had to change. Right, so if you want to share your age, you shall. I will call out your name, and so you know who it is. And if I don't hear an answer, I'll just, as I said, I'll move on, right? So I'm starting with me, I'm 64. Ethan, what are you?
17.
Okay. Ripkin, do you want to tell me?
21.
Ray, do you want to?
17.
Okay. Denise?
33.
33. Risa?
18.
18. Victoria?
16.
Logan?
16.
Logan, 16. Mason? Okay. Theo?
20.
Christian?
21.
Courtney?
21.
Rena?
19.
Joshua?
17.
Chris?
46.
Amanda?
22.
Oh, I'm killing your name again. Chemtai, I think I got it right.
Yeah, you did. 19.
Okay. Teresa?
18.
Petrina?
43.
Angelo? Brooklyn then?
16.
Connor?
17.
Bailey?
17.
17. And Jennifer?
38.
Right. I think I have a double page here, so I may have to scroll to the right. Oh, okay. Where was Jennifer? Angelo?
18.
Christian?
18.
Ju-Hong?
17.
And lastly, last but not least, Brenna.
16.
You forgot me, but I'm also 18.
I missed you. If you know I missed you, just shout out your age and I'll stick you at the bottom.
18.
80. Anybody else I missed in that scanning? Okay. So what we're going to do is essentially look at this data. What you can see is the kind of really rough data you've got. And there's a number of ways I could organize that, and we've seen some. Couldn't I just do a group frequency table, for instance? That would be a pretty common way to group it. Okay, but we're going to show you a thing called the stem and leaf. So, first thing you do in creating a stem and leaf is you look for the smallest and the largest. Now, it's a pretty common thing you do in many diagrams. I think the youngest we got was 16 and the oldest is me, that's 64. And you're meant to say, you don't look 64, you don't look a day over 80. Okay. Now, that just gives me a spread of what I'm going to do. I think in this particular case, I am going to do a stem and leaf where each stem is worth 10. And I'll show you how that works. You draw typically 2 vertical lines. And then you put down, oops, starting at the top typically, 1, 2, 3, 4, 5, 6. This piece of the picture is called the stem. And then you look at the data and you just scan through the data. And as you scan through the data, you use just the next digit. So I'm going to use red just because I want it to be emphasized. So you go 64, 17, 21, 17, 33, 18, 16, 16, 20, 21, another 21, and 19, a 17, a 46, a 22, a 19, an 18, a 43, a 16, another two 17s, a 38, an 18, oh shooting space, an 18, a 17, an 18, a 17, 16, and another 18. This data is very, very much in the teens. Would you agree? That's pretty obvious to see it. And the red numbers, very often called the leaves. So if you're wondering why is it called a stem and leaf, and this bit's called the stem and this is like the leaf. It's a bit like this is the tree trunk and this is some branches coming off it. Have you noticed that any given one of these numbers does represent one of these? And so you normally have to write down a little key to tell people what it means. And you just pick one at random. So I'm picking this one. 4/6 means 46. And you might say, well, it's obvious it means 46. Well, can you imagine that it was a different set of data? And this was 6.1, 1.7, 1.8, 3.8. Can you imagine it was data like that? Then wouldn't this 4/6 mean 4.6? So it could certainly mean different things in different contexts. For instance, see if this was 640, 170, and 210, wouldn't 4/6 mean 460? So it's quite adaptable, isn't it? What does that number mean? Doesn't it depend on what the key tells you it means, right? So you need a key so people can understand that. There is one unfortunate little hiccup with this data, and it just really involves a tweak. Does anybody know what I'm going to have to do to this data so that it's considered finished and ready to be used by some other person who's going to have to look at it? I'm going to recreate it. Yeah, you have to sort it in order. Now, a lot of my early data is in order, but none of this. So here goes. I should do it in blue. 1, 2, 3, 4 of you. So 1, 2, 3, 4 of you. 1, 2, 3, 4, 5, 6 of you. 1, 2, 3, 4, 5, 6 of you. 1, 2, 3, 4, 5 of you. And then 2 19s. That next one's going to be a lot easier. 0, 1, 1, 1, 2. Actually, bang in order. Tweak it a little bit. Nobody there. 64. So and it's normally a good idea to put a heading at the top of a stem and leaf so people know what you're doing here. I mean, is this the number of times that they didn't do their homework? Is this how many people are in their family or how much money they've got or whatever, right? So in this case, it's ages of those two students. Now, if this class, which I strongly suspect it's not, but if this class was a fair representation of OC students, wouldn't we be able to look at this data and get what basically an idea of the age distribution? You know, How many young students do we have? How many middle-aged students do we have? How many older students do we have, right? And here's another little cool thing you can do with this switch. Doesn't that look like a histogram? Stem and leaf are normally used as like at the beginning of your data. Can you imagine you were doing a science experiment and you were quickly writing down 30 or 40, you know, temperatures or 30 or 40 weights or whatever it was you were doing, right? You're just writing them down in your little notebook and you've got this raw data. There's our raw data. And you've got this raw data. And this might well be the first thing you do. And because what it does is, doesn't it allow you to get a visual picture of what your data looks like? What kind of groups, age groups there are. And so it's a very useful thing for that one particular situation. This particular version of it has got one row per stem. Sometimes your data, I'm not going to write all the data down, but can you imagine that we got data where it was 25, you know, numbers like 25, 26, 26, 33, 37, and maybe 41, where the numbers didn't vary very much, right? From the smallest to the biggest, there was only like 20 odd people. You couldn't really do a very realistic stem and leaf. If I tried to do a stem and leaf, wouldn't I basically just have 20s, 30s, and 40s? Wouldn't it just be 3 guys wide? And when there's only 3 stems, it's very hard to see a pattern, right? Because there's just not enough room to detect. Is it, well, actually, let's go back to this one for a minute. Do you know I would call this shape skew to the right? Remember the naming of histograms? Wouldn't this data be skewed to the right because the tail is to the right? Would you also say this data was probably unimodal? There's one blinking big hill, and that's all there was. If you only have 3 stems, isn't it very, very hard to tell anything about the structure? It's just too crushed. So what you do in a situation where the data doesn't vary a lot is that you do 2 rows per stem. So I want you to imagine not just this data, but can you imagine there's some other numbers, lots of other numbers. This is how it would work. You do 2 and another 2, 3 and another 3, 4 and another 4. In the first group of 2, you put all the 20s up to 24. And in the next group, you do all the 20s up to 29. And then in the 30s, all the 30s up to 34. And in the second group, starting at 35, finishing at 39s. In the last group, now in this case here, can you imagine this was also students, but maybe these are ages of students in the welding program? You know, because different subjects, you know, different kinds of age groups. So when I look at this set of data, can you see that that 25 means a 25-year-old? Doesn't that 9 mean a 39-year-old? But do you see how the 30s have been split into 2 separate groups? Now, by doing this 2 rows per stem, if I turn this side on, do you get a feel of what that histogram looks like? Would you agree it's probably unimodal? I'm not sure if it's skewed left or skewed right. I don't think I can say anything for sure about that. But at least I have got more real estate to see a pattern if there is one. Now, you can use this data, a stem and leaf, to answer a lot of questions to do with percentages of things. So I'm just doing a quick head count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Right, we've got 27 here. If I said to you, what percentage of OC students are teenagers? Right, what percentage are teenagers? Then I would just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And I would say 17 out of 27 times 100. And I could tell you 17 divided by 27. And it's roughly 63%. So about 2/3 of this class are teenagers. And I could say to you, what percentage of this class are over 50? Well, that's me, right? So 1 out of 27, which is about 3.5% roughly. Can we also say what percentage of students are between 20 and 30, right? 20 up to 30 or 20 up to 50 or any other group? Aren't all those kind of questions doable now, because you can just count the numbers much easier. If you had to do it with the raw data, wouldn't you have to keep checking that you never missed one, and you'd have to rescan everything over and over again? If you look at this data here, would you agree that the most common age group is 30-somethings? Right, would you agree the most common age group is 30-something? In fact, would you also agree that if you wanted to be a little bit more precise, isn't the most common age group the later 30-somethings, right? The 35 to 39 people. So for whatever reason, welders tend to be older, right? I'm making this up, but if that was true, that's what you'd say. Are we cool with stem and leaf? Are you cool with 1 row per stem and 2 rows per stem, and how they differ and how you would create them from that data? So as always, I'm just going to go and show you what that looks like in the homework, so that you can get an idea of, what do you do? Right, let's jump back a little bit here. Okay, I don't know how easy this is going to be for my brain, but I'm going to try it anyway. Here is some data which is to do with wetlands offer diversity, and it gives you a stem and leaf of these particular digits. So I'm looking at them. The smallest one I can see is 30. Smallest one I can see is a 9. Biggest one I can see is a 89. No, I can beat it. I can do a 90. Would you agree this then starts off from single digits up to including a 90? So I'm going to look at this, and I would start my table and do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can imagine filling in the rest. So what I'm doing right now is filling in the stem, right? 0, 1, 2, 3, 4, 5, 6, all the way to 9. Now, that number there gets a 9. 0 stroke 9 means 9, whatever. 42, well, 2, 3, 4, 42. Now it says use the 10 digits of the stem and the 1 digit as a leaf. Enter none if there's missing one. Can I just pretend that there are no 60s? And you'll type in none. If I was doing the teens here, I don't think I can see any teens. Do you see any teens? So that's another none. What is wrong with the 20s? That I'm deliberately about to do something wrong with the 20s. Hopefully it's a pretty obvious mistake.
It's out of order.
Or out of order. Now, doesn't that mean you probably need a little bit of scratch paper and write down all the 20s so you can put them in the right order? Or you can just type them as you see them and then reorder them after you've done it, but you got to do whatever you got to do. And so I'm sure that's not the only 20s, but if that was the only 20s, wouldn't that be the final result? And then these questions here, or these statements here, are to do with the guy up here. So it says here the percentages are concentrated between 60 and 90. I don't know yet. I suspect it's not, but you can find out when you do it. And you answer, yeah, that one's true. I'm making this up. That one's true and this one's true, you know, because you can have more than one answer that's right. There's a really big one. Put in the data. Skewed left, skewed right, bimodal. Oh, I did mention it some class. Unimodal is one hill, right? Sometimes called mound-shaped. What makes you bimodal? What do you look like if you're bimodal?
Two hills.
Two hills. Do the hills need to be the same height?
No.
No. You can have a big hill and then a little hill, you know, later. It has to be a noticeable hill. You can't just be 2, 1, you know, 2, 3, 2, you know, a little bump. That's really not counted as a hill. It has to be, you know, like a big hill and then 2, 3, 5, 7, 5, 3, 2, right? A distinct up and down pattern that lasts more than just a couple of numbers to be a real hill. Otherwise, it's just incidental randomness that you're going to get anyway. You know, you get that quite common. I think this is, yes, it is good. Here is one that you don't draw, but it has been drawn for you. It's called, at least I call it, a back-to-back stem and they call it a back-to-back. Good. And it shows you, well, let's do the depth part. In archaeology, the depth below the surface grade at which artifacts are found is very important. Greater depths sometimes indicate older artifacts. Yeah, I've seen documentaries, right, over in the 1800s, and then they dig a bit deeper and they say, oh, now we're in the medieval. And then they dig deeper and say, oh, now we're in the Bronze Age. You know, if a place has been there a long time. And it makes sense, doesn't it, that when arrowheads and broken pottery are left, dirt gets on top of it, and then, you know, 100 years go by, it's like it's 6 inches under the ground and so on. So here is site 1 and here is site 2. And if you look at this data, it's got a lot going for it. It's a little bit messy, but in site 1, 25, and in this side here, like 60 and 65 and so on. And these sites are basically telling you the depths at which artifacts were found. Now, if I look at this site, do you notice that at any given depth, weren't the artifacts found all the way down to 110? So now, every time they went a couple of more inches, they found something. And then on a couple of more inches and found something. What that would tell me here is that this site was inhabited continuously for a long time. Right? People lived in that house and they died and their grandparents or somebody else took over and that village stayed there. And, you know, villages have garbage and they throw it out and then it gets dumped on with new garbage and hundreds of years go by. But as you start being an archaeologist, isn't there going to be stuff all the time, all the way through? Do you see that there's a big gap here? If nothing happens, if a village just gets abandoned, doesn't dust get blown in and mud gets swept in and it slowly just gets, you know, covered with stuff. What that would tell me is that, see, this site was inhabited and then abandoned for a big chunk of time and then later on get inhabited again. So if you were looking at a Native American site where Native Americans were living, this one would be a continuously inhabited site, and this one would represent, oh, they had a community there, and then for whatever reason they left, right? We can't handle it, we can't eat, we got to move. And then later on, the weather changed or whatever, and they came back and they started the new place. If you ever get to Scotland, we have tons of history. And if you love history, you can't go anywhere in Scotland without bumping into history, right? You could literally go to somebody's backyard, and if you dug it far enough, you'd find something. And, you know, unless you were really unlucky. Because we've been a really long time. Okay, I've reached a very natural finishing point. I've covered everything that you need to know, I hope that you need to know, to do all your homework for this Sunday midnight. So make sure you get it done this Sunday midnight. If you aren't aware of this, because some of you had to join a class later than the day, then let me show you some resources out there that will be of help to you. So, a few seconds. Once I finish this, I'm going to do the ogive thing for those people who want to see an ogive again, right? Let's finish it. Right. I have two statistics classes. So what you will get is this thing here, right? This is, or should be, your Canvas site. If you click on class Zoom schedule and videos, you will see recordings of every video, including this one. If you click on chapter 1, you will see smaller videos on the same topics made by various people. And you'll also get there some PDFs that I've written and PowerPoints that you've got. So you can get other information if you're not sure about how you do something. Here you'll do chapter 2 stuff. That's where you'll find chapter 2 help, right? If you need a calculator, this is an emulator that you can use. This stuff down here is useful stuff, but it's only essentially for if you need financial aid or you need to get technology or something, you could click down there. Everybody cool? Right, could you say hello? Because that's registration. So you go down to the, oh darn it, you go down to the chat thing and you say, hi, how are you? Whatever. And that will be you. And if you're cool and you don't need any help with OGI curves, then goodbye. And if you want to, bye-bye. And for those who want to hang around, I will be here to talk about OGIs. Be with you in a few moments. I'm trying to find the right section. For some reason, I screwed up. Here we go. That's better. Okay. Almost done. I've got the right thing. I've just got all the answers, and that's very distracting. Should be able to do it without the answers. That looks better. Okay, so what you're going to be seeing right now is question 5 from the beginning of chapter 2, right? The first one, frequency charts and diagrams. We have a whole load of data here, and this data, at least in this one, would be used to create class limits, class boundaries, midpoints, frequency, relative frequency, and cumulative frequency. So there's a lot of stuff in this. We are going to, or I'm going to at least use this data to create an OGI curve. So from start to finish, essentially. So I probably will need to make this, now I thought about it, I'm going to have to make it a little bit bigger so you can actually see the data. Can you see the numbers now, most of you? Right, because I know what I'm like. I'm probably not going to, I'll miss a number. I've not got great eyesight. So let's start off with, how do you find the class width? Well, you're going to take all this data, all these numbers, and break them into 6 groups or classes. As I check this, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 6, 7. So there are 70 numbers being split into 6 groups. So I'm coming back out of this so you can see my calculation. So there were 70 numbers in that list, and we're being asked to break it into 6 groups. Right, miscount. I'm glad I caught myself. I know there's 70 numbers, and that's true, but that's not the calculation I should do. I was thinking of something else. What is, oh, darn it.
There's 11 in the class.
There's, oh, okay. Well, that's, yes. Okay, look at this data for me. What is the smallest number and the largest number? Because that's really what I need to answer the question, find the class width. So from this data that you can see, what is the largest number and what's the smallest number? And we can use that to get the class width. Okay. I can say 101. Can anybody beat 101 for the biggest?
109.
Okay. Can any beat 109 for the biggest in this data set? Okay, 109 gets the job. What's the smallest number? I see 45. Can we beat 45? We'll all agree 45 then?
Yeah.
Okay, we're going for it. So that's the calculation I should have been using. Largest take away smallest divided by how many groups you want. So in the question, they said they wanted 6. So I go to my calculator and I do 109. I subtract 45 and I get this number. And then I divide it by 6 and I get 10.67 roughly. Class widths must be whole numbers and always round up. So that means 11. So I'm going to do a class width of 11. That means there's going to be 11 numbers in each group. Right, so now I'm going to return back to that and start filling in that data. Okay, so 45. 11 numbers, I count with my fingers. 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55. Now, a lot of people will look at those two numbers and say, you got it wrong, that's 10, not 11. But trust me, there is 11 numbers there, isn't there? If you actually count them, there's physically 11 numbers in that group. You might count 45 to 55. There's 11. Imagine I said, how many numbers are there between 3 and 5? Well, you might say 2, right? 3 for 5, 2. We'll count it. 3, 4, 5. Aren't there 3 numbers? It's that kind of thing. Right, well, after you do that, it's easy to get the others. I normally just work on the first one. Make sure that's right. Every other answer for the start is just going to be 11 more than the last one. So I'm now going to do 56. And then the one after that's going to be 67. And then the one after that's going to be 78. And the one after that's going to be 89. And if I got this one right, I believe this one is going to be 90, isn't it? No, it's not. It's 100. Now I got it. Now, that guy is 55. Won't the next one be 66? Oh, this one's going to be easier. 77. 88. 99. The last one's a bit fiddly, but I believe you get 110, right? Are we comfortable with that? How we created those guys? Now, class boundaries. We will need class boundaries for the Ojai curve. So we need to do those guys. The class boundaries are easy. You take this number and you subtract a half from it. So basically 44.5. Don't know what helped there. 44.5. And then the biggest class boundary is 55.5. And if you're wondering what are those class boundaries represent, do you know any number in that range would round off to a value somewhere between 45 and 55? So once you've done those ones, you can then use the trick. Everything's 11 more than it was before. So 55.5. I keep hitting the wrong buttons. I think it's my eyesight. 55 point. Oh, come on. Behavior. There we go. What's that one going to be? 66.5. 77.5. 88.5. And 99.5. And then on this side, where are we going? 66.5. 77.5. 88.5. 99.5. And then 110.5. Have you noticed that when you do class boundaries, whatever number this finishes with, doesn't the next boundary start exactly at the same space? You notice that? That's a pattern that's true. I don't really need the midpoints for what I'm about to do, so I'll just do the first one, show you, you know what it is, but I'm not going to spend time on it because we don't need it for the ogive question. If you want to get the midpoint, you basically add the class limits together and you half them. You basically find halfway between the two. So I'm doing 45 add 55. Clear that out. 45 add 55. And then I'm going to divide by 2. And the answer I get for this midpoint is 50. And then everybody after that's 11 more. So you would get that. I don't need the relative frequency, so I'm not worried about that. I do, unfortunately, and that's going to be the slowest part of this process, is I need to get the frequencies. So I'll give you an option here. We can either get the real frequencies, in other words, count through the list and write down what there is, or can we just put down some random digits to kind of show you what you do? That can be quicker, but it's not going to be the correct answer. Do you want us to fight our way through?
Can I give you the correct answer?
You want the? Have you got the correct?
I have them already.
Oh, perfect.
I only need the chart part. At the
then
very
you are
end.
good. Let's use your number so we can do it. What you got from the top?
3, 7, 22, 26, 9, and 3.
Okay. Not that this matters. Did that take you about 10 minutes to do correctly? Was that a pain in the butt?
Yeah, it took me a really long time to get those
Right.
numbers.
So we've just saved a whole load of time so we can thank Jennifer. Right. Now, forget about the relative frequency. We don't need it for the OGI curve, but just so that we can do it as a complete thing, wouldn't the relative frequency for this one be 3 divided by 70 turned into a decimal? So here goes. 3 divided by a total of 70. I have 0.04. Do they have, 4 decimal places? Okay. So 0.0429 would be the 4 decimal place thing. And you do 7 out of 70, 22 out of 70, 3 out of 70 as a decimal. Here, 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 and here. So that would be the frequency thing. You've probably done that fine. Okay, cumulative frequency. The first one is whatever that is. The next cumulative frequency is what you get when you add the first 2 together. So that's now going to be 10. The next one is what you get when you add the first 3 together. So that's going to be 32. Then the next one is all 4. That's going to be 58. And then the next one is going to be 67. And I can tell you right now that I'm very pleased with your data. Why do I know that there's a great chance you did it correct based on the fact that the last one was 70? How do you know? I know, Jennifer, that you probably did it right.
Because it adds up to 70.
Correct. If it had added up to 69, doesn't that mean you missed a number somewhere?
Yes, and I did that once.
You're better than me. I would have done it 3 times, right? So you're better than me. But now you got it, you're good to go. So the part, all of this was leading up just to one job. How do you get this thing to become that thing, right? This is where the OGI curve is going to be done. And I'm going to just spend a few seconds writing down the bits of the table that actually matter for that. So you're just going to have to, I don't want to have to zoom up and down, because if I zoom up and down, I'm definitely going to screw up. So I'm just writing down the 44.5 to 55.5. And the only other thing I'm writing down is what the cumulative frequency for that guy is. And then 66.5, then 77.5, then 88.5, then 99.5, and lastly 110.5. And the numbers are 3, 10, 32, 58, 67, and 70. Now I'm going to show you a very crude version of what it looks like, then we'll do it properly on the software. The bit you're looking at that's important is this bit here, right? If you were doing it by hand and not doing it on the software, you would simply just take this data and along the x-axis, you would start at an appropriate number. Now, in this case, they happen to have numbers like 44 and 55 and 66 and 77 and what a horrible scale. 99 and 110, right? So the first number, the 44.5, you add that in. It's got a cumulative frequency of 0 because at that point, nobody is there yet. So can you imagine I go 10, 20, 30, 40, 50, 60, 70. So at 44.5, which is about kind of here, I do 0. At 55.5, I do 3. So that's about here, and 3 is about that. At 66.5, I do 10, which is about here. At 77.5, I do 32, which is about here. 88.5. Why does that look weird? Oh, because I missed one. There's 88. There's 99. And there's 110. So at 88.5, which is roughly about here, I'll do 58, which I'm guessing is about here. At the 99.5, I'm going to do 67, which I'm thinking is about here. And at the last one, I'm going to do 110. And basically, my OGI curve is what you get when you add or you join all those dots together. So that's the guy that we need to kind of do on the software. So can you get a rough idea of what it should look like when I'm finished? And that the key to getting it right is to realize that only the first interval and only the first value gets used, and it's 0. After that, it's the end numbers in your boundary tables. So now the fiddly part. This has to be done on that chart. Okay, 44.5 is a 0. I'm going to go, oops, the double dot thing. 44.5 is going to be there. And it's going to go to 0, done. And then the next number is 55.5, and it's 3. And 55.5 is about here, and 3 is about here. And I'm probably not that accurate. So if I click on this, 45.5 should be 0, and 55.5 should have been 3. So do you see I'm just tweaking my numbers to be in the right place? Now the next one is going to be 55.53 joined to 66.510. So got that guy, click on you. Oops. Got that. Got that guy, click on you. And then I want to go to 66.510. So 66.510 is probably here. Let's see how close I got. That's a good far. That was miles off. 66.5. And that should have been 10. I'm slowly building it. Can you see I'm slowly getting there? It's just taking a fair amount of time to do it. Right, the next one is going to be from that one left off, 66.510, and I'm now going to go to the 77.532, which I'm guessing about here. See how close I was. Got that one. Not too bad. 77.5. Done. Okay. Just keep going. Start off at that point and then get to 88.558. 88.558. There. Okay. 77.532, good. 88.558. Oh, yeah, I hit a button here I didn't mean to hit. 58. Keep going, we've only got a couple left. There's the 88.5 guy, and that now goes to 99.567. That's miles away. 99.567. It's about here. Let's fix it. That should have been 88.5. And it should have been 58. And the next one should have been 99.5. And it should have finished as a 67. I'm getting these numbers from that big horrible piece of paper that I have written down. And at last, start at this guy and finish at 110.570. 110.570 is probably about here. Let's make it work. That 100 should have been 99.5. And instead of 68, it should have been 67. And the other one should have been 110.5. and it should have finished on 70. God in hell, that's a lot of work. Can you see the classic Ojai shape? Kind of goes up and it flattens off. You don't look happy, Denise. Are you okay? You'll be able to do it. It's not that many questions, right? I'm trying to give you a justification of wanting to do this, and the only one I can come up with is, if you do only a couple of these by hand, if you ever see one drawn by software, will you appreciate that you know where the numbers came from and how it got there, but you're glad you didn't have to do it yourself, right? It's a bit like that. So it's helpful to do it by hand, only to get in your brain how the process works. But in practical real life, if you ever wanted to do an Ojai curve, wouldn't you probably just go to a piece of software and say, make one for me, please? That's as far as I want to go, and that's actually